Hello, everyone. I am Ahmed Muhammad Abdelmonem, research scientist at KAUS, and I'll present to you our work on a statistical-based gradient compression technique for distributed machine learning. The recent growth of machine learning have led to several things. Larger data sets, we are now using ever-growing larger data sets, and therefore we are using also larger models to train on these large data sets. Therefore, training these large models and datasets takes significant amount of time. As reported recently by OpenAI, computation needs has increased by 300,000x since 2012. And the computation gains of recent latest hardware generations are not able to keep up with this. So one would wonder, how can I speed up my training? Specifically, what we can do is scale and parallelize our training job to utilize distributed set of nodes and their computation resources. However, the main bottleneck for this is the communication. In distributed training, communication takes significant amount of time due to the size of the models. So compression have been proposed as a way for communication reduction. In a compressed communication, the workers would compute their local gradients, and they exchange the compressed gradients by performing compression. And afterwards, they would update the parameters using the uncompressed gradient. So now compression would reduce the time, but this is dependent on how efficient is your compression technique. So because the compression and decompression take off the iteration time. So we need to also reduce compression overhead and the time. Recent work on gradient compression proposed sparsification methods, which sends a subset of the gradient, which are the most important values in the gradient. However, TOP-K as one of the methods is computationally expensive, and even the optimized versions of it are still slow. So threshold estimation methods for TOP-K have been proposed, where they try to estimate the minimum of the TOP-K values and use that to filter the gradient. Several methods have been proposed recently, like DGC, RedSync, Gaussian, KGD. However, the model accuracy is highly dependent on how efficient is this estimation or the quality of their estimation. So our contribution is that we find that existing work in gradient sparsification either ignore the computational efficiency of the compression methods or fail to estimate the threshold with acceptable accuracy, and therefore the convergence is not guaranteed. So in this work, we try to answer this question: how to efficiently find a top case threshold with high accuracy. So we propose SITCO. SITCO, in a nutshell, depends on the concept of compressible gradient. We verify that DNNs, the gradients of DNNs satisfy the compressibility property, and more details are in the paper. Also, having a compressible gradient, we do gradient fitting using one of the sparsity-inducing distributions. These distributions promote sparsity and give good model of the gradient. Then after this, if the threshold is not good enough, we go through several stages of threshold refinement until we get a high accurate threshold. This typically would require a few stages to reach that value. So SITCO in practice, we evaluated it in over several ML benchmarks using CNNs, RNNs, and different data sets. And here I'm showing one of examples, training an LSTM model on PTB dataset. And as we can see from this left-hand figure, we showed the normalized training speed up of the method compared to comparing SITCO with other methods. And we can see it can achieve up to 41x improvement compared to no compression baseline. And compared to the existing threshold estimation method, the SITCO can achieve as good as estimation quality of the threshold as good as DGC, which is the best method. And it shows that RedSync and Gaussian KHGD cannot converge to the target accuracy due to their bad estimation, as shown in the right-hand figure. So in summary, SITCO is, we find that threshold methods achieve low compression overhead. However, estimation of the top case threshold is non-trivial without doing any sorting, especially for the tail values. And changing gradient distribution during the training makes things worse. So in this work, we exploit the statistical properties of the gradient and try to fit the gradient using a sparsity-inducing distributions. And also we implement a multi-stage estimation to refine the estimated threshold. Our evaluation showed that Statistical can achieve significant speed up. Specifically, it can achieve 41x compared to the no compression baseline and 2x compared to DGC. It can achieve so with very high estimation quality, as good as DGC. Thank you. And for any questions, please reach out to me.